What's up, everybody? It's Dan from sagemathtutoring.com, and I'm here with another video, this time pertaining to improper integrals for the AP Calculus BC exam. So there's a particular problem that I went over with a student yesterday, and the problem itself wasn't too bad, but it did raise some questions. Okay, so let's take a look at the problem now. So let's say we are challenged to find the integral of this right here. Well, first of all, hopefully we recognize that we would be setting this equal to the limit, and we could say as b approaches infinity from 0 to b, and then we could just kind of rewrite the whole thing. All right, so that's a technique that's important for these. And from there, it would be a matter of recognizing that this is of the structure of the derivative of an arctan. So let's take a look at that. So the derivative of arctan u equals 1 over 1 plus u squared, and therefore it stands to reason that the integral of this would be arctan of u. All right, so you can kind of go backwards with it. Now you may notice that this structure does indeed resemble this structure. However, we have a variable squared. Maybe we can think of that as the x squared. But then we have this 9, which is clearly not a 1. So the question is, how can we sort of make this look like this on the bottom? There might be a way to do that right away. Now, what I'll do is I'll just rewrite the bottom so it says u squared plus 1, right? Because that's a little bit more in line with what's written here. Now, the trick is we have to essentially force this 9 to be a 1, right? And in order to do that, what we could do is we could rewrite the entire situation, only with a 9 sort of factored out on the bottom, right? And that would therefore be 1/9 x squared plus 1. Now, in that case, we have actually gotten a little bit closer to resembling this, right? We do have a perfect square plus 1, and over here is also a perfect square plus 1. At that point, we can bring the 1/9 out to the front, right? So we could say the limit as b approaches infinity with a 1/9 here. And I'm also going to represent the denominator as something squared plus 1. Because remember, this is something squared plus 1. Well, we have to ask ourselves, well, what's being squared to give us a 1/9 x squared? Well, what's being squared is a 1/3 x. That's what's being squared in order to give us this 1/9 x squared. So now we are adhering to this structure where it says something squared plus 1. We have something squared plus 1 there as well. Now at that point, we are ready for u substitution. We could then say that u is clearly 1/3 x, right? Not 1/3 x squared, but u is the actual number that's being squared here, right? And then we can say, okay, du is therefore 1/3 dx, and then dx we could say is 3 du. Now at that point, we are ready to sort of substitute all the values in that we have to. I'll rewrite this part. So we have the 1/9, we have b, we have 0, we have u squared plus 1, and instead of dx, we'll write 3 du. Okay. Now, at that point, I think my student would understand that that 3 could really go out front. So this is going to become a 3 over a 9, which is just 1/3. So that's going to be limit as b approaches infinity, 1/3 from 0 to b, okay, du. Now at that point, we can then actually perform the integral where we say the limit as b approaches infinity of 1/3, and we could say arctan of u, right? And we have our b and our 0. Now our u, of course, happens to be 1/3 x, right? So I'll write that down here. That should be an arrow. I always forget to draw that. 1/3 arctan. I'll just call it x over 3 from 0 to b. Okay, so that is definitely making progress, right? So at this point, we are ready to go ahead and say the limit as b approaches infinity of the following. It's going to be 1/3 arctan b over 3 minus arctan 0 over 3. And it's still, the limit right there, right? So at that point, if you were to plug in infinity for b, it would become 1/3 arctan of infinity over 3 minus arctan of 0. Okay, so we could ask ourselves what these are. Now, obviously, this is arctan of infinity, so let me sort of represent that. And I'm going to give the answer, and then I'm going to provide some more explanation on top of the answer. So with regards to the arctan of 0, that's not a theta, but a 0, you have to sort of ask yourself, the tan of what angle equals 0? All right, that's a sort of a good way of seeing it. The tan of what angle equals 0? Well, if you look at the graph of tangent x, well, clearly we can see that the tan of 0 equals 0, right? So the tangent of 0 is also equal to 0, so therefore this is minus 0, okay? Now, similarly, we could say the tangent of what angle is equal to infinity? Well, do you see how it shoots up to infinity here? That corresponds with this angle called pi over 2, okay? So ultimately, this is going to be 1/3 pi over 2 minus 0, which is therefore just going to be equal to, put little equal signs here. That's going to be equal to pi over 6. Now, the question can arise, as it did with my student last night, as to why are we only paying attention to this part of the tan graph when we're performing that analysis, okay? Why are we only paying attention to this part of the tan graph? Well, it is seemingly the case that we could have just as easily paid attention to this part of the tan graph and said, okay, the tangent of what angle equals 0? Well, why not pi? And the tangent of what angle equals positive infinity? Well, why not 3 pi over 2 due to this part, right? And the explanation is because we need to remember that even though I'm using this tan graph as, a reference, at the end of the day, we are dealing with a function called arctan. Now, arctan does have its own graph, which I could present to you shortly. And many students have learned the arctan graph, but it is the case that they have spent less time on that graph than they've spent on the tan graph, okay? But we do need to keep in mind that the function we're actually dealing with is arctan, and in order for this function to be a function, it needs to be the case that this tan function, which is the inverse of arctan, this tan function needs to have a restriction on the domain. And what mathematicians do is they say, okay, if we're going to have conceptualize arctan as a function, well, we need to place a restriction on the inverse of arctan, which is tangent, and the restriction on the domain would be from negative pi over 2 to positive pi over 2. So mathematicians choose to only pay attention to this part of the graph, okay, when it comes to the tangent function. And therefore, if you have a restriction on the domain of the tangent function, then we can say that the arctangent would also be a function. Now, before I show you the graph of arctan, let's think a little bit more about this. Anytime you have an original function and then you're considering the inverse, the original function only has an inverse if the original function passes the horizontal line test. Okay, not the vertical line test, but the horizontal line test. So I'm going to say that again. A function like this only has an inverse if it passes the horizontal line test, meaning if you are to put a horizontal line through this thing, it needs to hit the graph at only one place. Well, if you have all these other shenanigans going on, well, this thing is going to fail the vertical line test, right? It's going to fail the vertical line test. As you pass the vertical line, it's hitting numerous parts of the graph, right? Whereas if you sort of get rid of these other parts of the graph, which I'll do right now, it's going to not look that great, but if you get rid of all these other parts of the graph and you literally just restrict the domain of the tangent function, well, then you should be able to pass, a vertical or horizontal line, through it, and you're only hitting at one place, right? Let's just disregard that part that I didn't erase very well. Okay. All right, but you get what I'm saying. So now it passes the horizontal line test, right? Once we've restricted the domain, it passes the horizontal line test. So therefore, we can say that this function does indeed have an inverse. What do we call that inverse? Well, we call that inverse arctan, okay? Now, because we've restricted the domain, we can now say that this function has an inverse. Now, let's take a look at the actual graph of arctan right now. So the graph of arctan looks something like this, and I do want to add that these go on forever, both directions, and it so happens there's this sort of asymptote associated with pi over 2, all right, and negative pi over 2. And this, you could see, would be the inverse function of this graph here, if you kind of pause the video and think about it. In other words, every so-called x value and y coordinate on this graph are reversed, where the x coordinate of this graph becomes the y coordinate of this graph, the y coordinate of this graph becomes the x coordinate of this graph. And if you were to pause the video and kind of inspect that, you would see that that's definitely the case. Now, had we had memorized the arctan graph, well, then this answer would have been very easy, right? In other words, arctan of infinity. In other words, as x approaches infinity on the arctan graph, you could say that y approaches pi over 2. And that's clearly happening here. Okay, so a case could be made that it actually would have been better for us to have utilized this graph to understand what arctan of infinity was. But again, I alluded to the original tangent graph because that is a little bit more of a common graph. That's probably a graph that most students have certainly memorized, whereas not all teachers spend a lot of time on this graph, so I don't expect all students to kind of remember this one, but it does check out. All the information checks out. And let's double check this, might as well. The arctan of 0, well, that's clearly 0, right? And that's why the answer is like that. Now, let's kind of take a look, just for a bonus, let's take a look at how this phenomena of restricting the domain of an original function allows us to have a graph of the inverse function. Let's look at how that relates to sine and cosine as well, just to really hammer this point home. So here's the graph of sine. Many people are sort of familiar with this one. And notice how this graph cannot have an inverse unless you restrict the domain. And the reason is because if I draw this horizontal line here, and I pass it over this sine function, look, it fails the horizontal line test because it's hitting here, 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 and here, right? So that's a problem. It is for that reason that we would have to restrict the domain on this in order for this thing to pass the horizontal line test and therefore to have an inverse. So we could say that the domain, and what mathematicians say is that they restrict the domain only to this region here that I'm going to sort of highlight. Okay, right there. Now, if you think about it, that region would indeed pass the horizontal line test, right? That region between negative pi over 2 and pi over 2, okay? So therefore, we could say that the sine function with a restricted domain from negative pi over 2 to positive pi over 2 does indeed have an inverse function called arcsine, right? So here's the graph of arcsine. All right, here's the graph of arcsine. Now let's kind of analyze this situation. First of all, we know that the range of the original sine function goes from -1 up to +1. So that should be the domain of the inverse function. So is that indeed true? Well, yes, the domain goes from -1 to +1. Now, the restricted domain of this function was from negative pi over 2 to positive pi over 2, which means that the range of the inverse function, also known as arcsine, should be between negative pi over 2, which is down here, and positive pi over 2. So that is, I'll draw a little thing here. It goes from there, the range goes from there to about there. And that is, we could say, negative pi over 2, which is like, what's that, negative 3.14 divided by 2, right? Seems like it should be around that, around negative 1.5, similarly with positive 1.5, right? So everything I'm explaining right now should also help people understand why the graphs of inverse functions are kind of like often weird looking. Inverse trig functions like this are kind of weird looking, where it's just like a little thing like that, and that's all there is to it. Now, granted, that arcsine function went forever, right? But this one is kind of like, it's just this part, and it is, the reason for that is because of the restricted domain here. Okay, so let's look at cosine. Okay, so here's the graph of cosine, right? Now we need to ask ourselves, well, this thing certainly, seeing as how this thing certainly fails the horizontal line test, right? Because if we drag this over it, well, we're hitting in numerous places, right? So what is the domain that we should restrict this to? And what mathematicians have decided is that they're going to restrict it to this domain here. Okay? We could say from 0 to pi. And the reason for that, of course, is because that would indeed pass the horizontal line test. But the moment you get outside of that, well, then we have a problem, right? So, therefore, the arc cosine graph looks like this. So, as you can see here, this also is just like sort of limited looking, right? But note how the domain of the restricted region is from 0 to pi, which is going to be the range of the arc cosine function that goes from 0 to pi. It's also the case that the range of the original cosine function goes from -1 to 1, and therefore we can clearly see that the domain of the arc cosine function also goes from -1 to 1. So hopefully that makes sense. For my student who's watching this, that's the explanation for the answer to that problem we worked on, where we find the integral of 1 over x squared plus 9. So anyway, hopefully that's helpful, not just for my student, but perhaps for some others as well. And I will talk to you all later. If you have any questions, just comment below. Thanks.